Hey, welcome back. So we're into Honors Pre-Calculus. Monty here. Week 33, May 17th to the 21st. So we're right in the middle of May. What are we trying to accomplish? Last week we discussed, don't forget our pre-calculus team, we discussed the idea that we're wrapping up the pre-calculus piece because in the last 5 weeks of school, let's focus on getting ready for calculus. That would be the most important thing because most people that take pre-calc at this level in high school are pushing for college credit in calculus. Okay, so don't forget in our team page is where we post the videos. We also have the stream channel for the videos. If that doesn't work for you, that's okay, because let's go find the internet. Digital tools, Clever, Blackboard, and our actual pre-calc class. So in Honors Pre-Calculus, in the announcement page, we just keep piling them on top of each other, so all the announcements just pile up with the videos week by week by week with whatever cheat sheets we have. I mailed home the actual quick study laminated for Intro to Pre-Calc, the calculus piece. It's on the pre-calculus one and then the calculus one to help out, because it's a different way of talking. Okay, instead of thinking of instantaneous moments in time, everything is average. Okay, how do we get velocity? How do we get acceleration? How do we get instantaneous? What are all those differences? And last week I made the comment, we want to go down to Intro to Calc, and each week we want to push ourselves to watch every one of the videos. Okay, so let's think about that again. So 9A, limits in motion, 1, 2, 3, 4. B, 1, 2. And derivatives, 1, 2, 3. Okay, so here's 3 items. So if last week and this week we did these, and then Memorial Week we do limits, and then in June we'll do the basics to derivatives. So last week and this week, around Memorial Day, and then in the month of June. Okay, so that'll kind of break that up. Now let's go to our actual pre-calc class, and we go down to limits in motion and area. So this week, Memorial Week, limits in basic derivatives. So this will be the June in here. This will be Memorial Day, and so today. Okay, so I'll let you watch the videos for limits in motion, a couple of them last week and this week. Take notes, okay? Because this is what we're talking about. This is an instantaneous change right here when it's a point, or we average over time, okay? The slope of the line over time, which leads right into limits, motions, and tangents. So let's look at this very first problem, okay? And I better turn on the whiteboard here. Okay, a cyclist travels 10 miles in an hour and 15. What is her average velocity for the entire period of time? Okay, so again, the study of calculus. Okay, so we're going to have time, and we're going to have distance. Okay, and you go on a bike ride, right? And just for fun, as you travel through time, you cover distance. The more time, the more distance. Well, what if that wasn't linear? What if you changed, right? You went up a hill, down a hill, stop sign, consistent, up, down, over, right? What if that was your curve? Okay, So now our time is an hour and a quarter. So let's call this, let's see, 1 hour, and this is a quarter of an hour, right? Okay, and we traveled 10 miles, okay? So this would be 10. So we traveled 10 miles in an hour and a quarter, sorry, an hour and a quarter, okay? So total time is 1 and a quarter. Total distance, and most of the time in math, S is for distance, okay? So the average velocity. And if you remember your physics, velocity is distance divided by time, right? And you think of distance over time, meters per second, right? Feet per minute, right? Miles per hour, okay? All these different rates. All right, so average velocity is the change in distance over the change in time, okay? So now that I did that, let's just see what the computer tells us, and they actually have a video on this one, so that's kind of cool, so you could watch that. So let represent position, let S represent the position, and T represent time. The change in S, the change in distance over the change in time, and they converted it to a decimal, fine, and they divided it, change in S over change in T, okay? And they got an answer, 8 miles per hour. All right, so let's use ours. 1.2, so in ours, velocity average is the change in time, change in distance. 10 miles time 1.25 hours. So miles per hour, so 10 over 1.25 mph. Let's grab a calculator. Over 1.25, okay? And we get 8. So in our case, we're going to get 8 miles per hour. And what we created was the average between the 2 points in time, okay? So all of the instantaneous could be different, right? We could have had a curve like this, we could have had a curve like this, right? So, but we found the average. Let's see if 8 works for us here. Cool. All right, so feel free to wander through those problems. We're not in a hurry, okay? And what is this? Determine whether the statement is true or false. A ball rolls down a ramp. It's instantaneous velocity. Instantaneous velocity is always 0. True, since no force was applied to the ball, the instantaneous velocity is 0. False, the instantaneous velocity is the same as the average velocity. If the ball has changed motion, the instantaneous velocity is non-zero. True, a ball always rolls down a ramp at a constant rate. Therefore, instantaneous velocity is 0. The instantaneous velocity is the limit of the average velocity. It is non-zero when the ball is moving. So, what I always like to do when we have problems of concepts, let's think of this, okay? We got this ramp, right? Ball rolls down a ramp, okay? So here's our ramp. So we got a ball. Okay, we let the ball go. Ball's going down the ramp. Ball's going down the ramp. Ball's going down the ramp. okay? And it's accelerating, okay? And thinking of, in Algebra 2, in quadratics, gravity is 32 feet per second squared, or 9.8 meters per second squared. All right? So gravity, the ball is rolling, the ball is picking up speed. So now, time, distance. Not covering very much distance, and then it covers more and more and more distance, right? So let's redo that. Okay. So from here, okay, so now the distance. Okay, when it first starts, it's not covering very much distance, right? But by the time we get to this point, it's covering more distance. Horrible. Good Lord. Maybe something like that. Can you see how it's going to grow over time? I don't like that there. Something like that. Okay? Now, instantaneous velocity, instantaneous is a certain point in time. A certain point in time. A certain point in time. So now, just to kind of redraw these, instantaneous, 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 right? So it's going to keep getting bigger and bigger and bigger. Well, instantaneous velocity is always zero. False. Instantaneous velocity is the same as the average velocity. No. Can't be, because average velocity, we just saw, is like that. It's the sum of the flat and the steep. The instantaneous velocity is the limit of the average velocities. It's non-zero when the ball is moving. I really like, careful. I really like D. But before we go on, let's check. Okay, so this one doesn't have a helper. Okay, so let's check this one. Yeah, okay. So, is the limit of the average velocities. Okay, and that's what we're introducing, is this idea of limits. Okay, so let's see if we can look at that. The limit, so this instantaneous, instantaneous, instantaneous. Okay, that spot, and that spot. The limit as we approach from this side, as we approach from this side. As we approach from this side, as we approach from this side, as we approach from this side, as we approach from this side. This is a concept that we're introducing. Okay, so take your time on these. We're already in 13 minutes and we did 2 problems and didn't even watch a video. I'm curious what the next question is. Okay, at x equals 3. Find the estimated slope of the tangent line of the graph. Okay, so as we approach, so let's blow this up. Okay, and at 3, okay, so we have this spot right here. As we approach from this side, as we approach from this side, 3, 4. Select the next choice. The slope of the line is about. Okay, so as we approach 3, can you see this line right here? So let's try to sketch that. No, don't do that. Okay. Alright, now I'm going to move this over right there, okay? So now, okay, It's about that slope. So the rise over run at that spot. Okay, at that spot, we're at 3, 4. Okay, and I wonder if this would be easier. See if it'll let me snap that. Awesome. Awesome, awesome. Okay, so now, right there, I'm going to cheat from there to there to there. 1, 2, 3, 4 over 1. Up 4 over 1. 4, slope of 4 units. I'm going to see if 4 is allowed. Cool. Okay, instantaneous velocity. And then we can talk about approaching, right? Viewing and calculation, estimate the derivative of the point, interpreting the tangent line. Okay, so in this one, good. So they've got an example. Walk through how we have the original curve. Okay, boom. Then we want to know at x equals 1 what the slope of the line is. Okay, and this introduces a new concept. So this is what we just did. The first thing we're going to do is graph this equation. X squared minus 3x plus 4. After we graph it, we evaluate it at 1. Okay, and I'm going to and we'll clear this, and we're going to go x squared minus 3x plus 4, and we graph it, and then we're going to evaluate it at 1. Okay, we want to evaluate it at 1. So when we go second and we look at the 1, it's a 2, but what does that mean to us, right? And how does that help us in this case? Use the graphing tool to graph the function. Okay, so we've got this graph. We're going to put that here, and I always like the y-intercept first. So at the y-intercept, 0, 4, 1, 2. See if that's enough. 0, 4, 1, 2. So click parabola, 0, 4, 1, 2. 4, 8. 4, 8. I think I saw 4, 8. 4, 8. Okay, so I needed 3. I graph it. I'm going to save it. Now, at 1, we want to know the slope of this line. Okay, and we can see that it looks like this. Now, I'm going to tell you the actual answer to this problem. Okay, we're going to learn that x squared minus 3x plus 4, y equals that. We're learning dy dx is the derivative. And it turns out that it's 2x minus 3. We learn that it's going to have a slope of 2. Okay, 2x minus 3, 2x minus 3. X minus 3. Use the graphing tool. Estimate the derivative of the function at the given point by interpreting it as the tangent line slope. At 1, at x equals 1, the slope -2. In our case, at 1, I'm going to zoom in. At 1, boy, it sure looks flat. Sure looks like I go from here to here. I'm going to say 1. Okay. The slope at is -1. I'm going to try -1. Yep. Sure looks like a -1. Okay, and then we do it again and do it again. All right. 20 minutes in, you can see how this is a slow process. Talk to you later. Skip this. I'm not ready for that yet. Have a great week and embrace the newness. Bye-bye.